Okay, now we're going to talk about open circuits. Okay, hopefully this be quick. This slide says, no matter how much voltage potential there is, no current can flow if there's no path for the voltage source to ground. In other words, if we do not have a path from battery to ground, it's an open somewhere. Current will not flow. You cannot have a circuit operate there's an open, break, interruption in a circuit. Any circuit in which there is no complete path is said to be an open, but not all opens are bad, because you can have an open ground switch that controls the circuit. It's supposed to be open until you engage it. You got switches, transistors, which are inside modules, relays. Usually they are normally open and controlled by something to close it to activate a circuit. Now, here's another thing. People get this confused. Let's go back to your car battery. You see the car battery is connected. It's on the battery, the post, the cable all connected. But it has this green crud on top of it, green on white crud on top of it. And your car don't start. You know that corrosion between that post and cable causing an open, non-contact? That's an open circuit also. Corrosion or resistance can cause an open circuit. While completely open, a circuit has infinite resistance. Any extra resistance in a closed circuit is a partial open. A complete open circuit allows no current to flow. That means there's no connection at all. I can have a lot of corrosion between 2 points, center cable, center post, and a battery cable, but they're not touching. That's an open. But a partially open circuit reduces current flow in a proportion to the unintended resistance. The great example for that one is a wire. I have a wire. I should have had a wire to show you. It's like a wire. There's a wire right here. Can you see this wire? Oh, you can see this wire in there. Yeah. You see this wire? There's a wire here. I don't know if you can see it, but it looks like it's connected. But internally, they have thousands of strands in there. If one strand is connected and everything else is disconnected, that's a partially open circuit. Unintended resistance drops voltage. Remember, any type of unwanted resistance, you're going to have a voltage drop across it, because we got to push the current going across it. It reduces current flow, so less voltage and current are available to do the intended work. Starter, fuel pump, light bulb. You'll see components that won't work all work at reduced output. Like a light bulb might be dim. A starter motor may move slower or not turn at all. A fuel pump may start the car up, but the fuel volume is so low, I have a high speed hesitation. Example, dim lights, slow motors. Refer to voltage drop testing. We already talked about it, right? Oops. So let me find another like example. Now look at this. This is a wiring diagram. Horns. Here's my voltage supply going through a switch that's normally open, which is normal. Once the side engages, it pulls the switch over. It's going to send voltage to both lights, to ground, and the horns go off. Again, this is a normal open circuit. My protection device, my power source, my control. But look at this side. Remember, as we said on the previous slide, this side won't work unless this side engages. So we have voltage going through this connector, through this coil, and out here to the integrated power module. It needs to have a ground for this. My ground is down here at the horn switch. When you're driving down the street, this switch is open, which is normal. If I put a voltmeter on this ground path, and this is the ground, This is the ground side. Remember, here's my load, that's voltage. You gotta remember this, it's gonna be on the test. This is a ground, oh, sorry. This is my load. This is the power supply. This is the ground. All this is ground. Another way you can think about this, if I have power on one side of the load, which is this, that little symbol is a resistor, that's the load. This whole side has to be a ground, and vice versa. So if there's power here, and I got my load here, this side has to be a ground. So I'm going to the integrated power module, coming out here, and this open ground just sits there. Now since it's not engaged, there's no voltage being used, there's no drop being performed. So if I put a voltmeter right here, at this point, the car's key on, engine off, or running, I put a voltmeter right here on this dark green violet wire. Oh, I never mentioned that, did I? DG dark green / VT, that's a trace. Anytime you see something like that, solid wire trace, dark green violet, the dark green wire with a violet trace going across it. So if I put a voltmeter right here at this terminal here, key on, engine off, or running, I'm gonna see system voltage on the ground wire. When you don't have, when you see system voltage on the ground side of a circuit, you don't have a ground, because it didn't drop yet, because we didn't engage it, because this switch here is normally open. So 12 volts or system voltage on the ground side, you don't have a ground. So, but as soon as I engage this, that voltage is going through the switch to ground. Magnetism happens here. Pull the switch over, the horns go off. So again, voltage on the ground side until it's needed. Once it's needed, that 12 volts drops to near zero. So if I have an open on the ground circuit, you do not have a ground. Peace. I'm out.